At the beginning of the drop, the acrobat is at rest, so the sum of the forces is equal to 0. Ft minus Fg is equal to 0. That means Ft is equal to Fg. Ft is equal to the mass times gravitation, which is equal to 646.8 newtons. There's also gravitational potential energy before the drop. μg is equal to mgh. Gravity is equal to 9.8, mass is 66, and the height is 8 meters. The gravitational potential energy is 5,174.4 newtons. At the start of the drop, the sum of the forces is equal to ma. The forces Ft plus Fs are going in the same direction. Minus Fg is equal to the mass times gravity. The static friction of the acrobat is calculated, and it is 0.234. During the drop, the only force acting on the acrobat is Fg, which is equal to mg. So Fg is equal to 646.8. At the end of the drop, once the knot tied around the acrobat's leg unravels, the force of the tension stops the acrobat and flips her around because the acceleration is so high. After the drop, due to rotational kinematics, the acrobat is flipped around. The work done by the acrobat for the whole drop is equal to 1/2 mv squared, which is equal to 3,169.32 joules. This is the work done after the drop. We also calculated the angular speed of the acrobat by using the equation v is equal to r angular speed. We used the height of the acrobat, which is the diameter, and divided by 2 to find the radius. The velocity is equal to gravity, which is equal to the radius 1.702 times the angular speed. The angular speed was calculated and is 0.174 meters per second. This is the angular speed of the acrobat at the end of the drop.
Thank you for listening to our physics project. This is Luke Turner and Danny Williams.